Today we're going to work a little bit with some applications of first order linear differential equations. We're going to talk about how they relate to mixing problems, which have a lot to do with concentration, and it's going to be really cool. So let's move on. Okay. First thing that I wanted to point out here is just that I'm excited to work with you guys and go over this problem. I also wanted to just share the question with you that we're going to work on today. So here's the question. Okay, so let's imagine that we're given a brine solution of salt, and so it's just basically a mixture of water and salt. And let's say that it flows at a constant rate of 8 liters per minute into a large tank that initially holds 100 liters of a different brine solution, which was dissolved in half a kilogram of salt. And then this solution inside the tank is going to be stirred and then flow out of the tank at the same rate that we have it being poured in there. Okay, now the question is this: if the concentration of the salt in the brine which enters the tank is 0.05 kilograms per liter, then what do we do to determine the mass of the salt in the tank after t minutes? Another reason this is going to give us an expression in the end is just because the concentration is kind of out of our control. Since the rate at which the different brine is entering the tank and leaving the tank is the same, we can kind of control the volume of water that's in the tank, right? Like it's constantly going to be 100 liters, but we can't control the concentration of the liquid inside the tank with respect to time. And so that's why we need to get an expression in terms of t minutes. And then it also wants to know when will the concentration of the salt in the tank reach 0.02 kilograms per liter. And so we'll take a look at that as well. Okay, now the first thing you do when you approach problems like these is you write down some key info. So let's take those little pieces out of the question here and write them all down in one place. So far we know the flow rate of the liquid coming into the tank to be equal to 8 liters per minute, right? The liquid entering the tank enters at a rate of 8 liters per minute. We know that we have an initial amount of salt in the tank of 0.5 kilograms. That's going to be applicable pretty soon here. We know that the rate at which the liquid leaves the tank is proportional to the rate at which that other liquid enters, right? So it's going to be a different liquid leaving than the liquid that enters, but they're going to leave at the same rate. And then we also know the concentration of the salt inside the solution that is entering the tank to be equal to, that's actually incorrect, it's 0.05 kilograms per liter. But that's okay, it should be fixed on the next couple slides here. So, okay, now let's recall a couple of things. Let's recall that concentration is equal to the mass of a substance divided by its volume. If we can figure out the ratio at which a certain substance is in comparison to a volume, then we can come up with a concentration or some sort of a frequency for that substance. Okay, or we also know that mass is going to be equal to that concentration times the volume if we wanted to manipulate that formula a little bit. Okay, and we also are given this piece of information here. Now, where did I get this from? This is kind of a big long formula and it doesn't exactly make sense right off the bat here if you're not familiar with problems like these. Basically what it's saying is it's saying that the rate of change of the salt in the tank with respect to time is equal to the rate at which the water of one solution flows in multiplied by the concentration of that rate minus the rate at which the liquid is going to flow out times the concentration, which is a different concentration of the liquid flowing out of the tank. Okay, now that was kind of a mouthful. I'm having Q represent the amount of salt in the tank at any given point in time, R represent the flow rate for the water in and out, and then the C represent the concentration. And now this expression Q of T over V0 plus R in minus R out. Where did I get that from? That's just going to be equal to the amount of salt in the tank divided by the variable volume, if that was the case. Right now in this problem that isn't the case, so we don't really need to worry about it. We just need to take that initial volume V0 of 100 liters, and we need to take our expression Q of T and divide it by 100 in order to come up with that concentration for the substance that's going to be leaving the tank, right? Because that concentration is going to be variable. We don't have any information on that right now, and this will be our expression. Okay, knowing and keeping all of that in mind now, what we're going to do is we're going to go ahead and solve the problem using this model that we've come up with for first order linear differential equations and their application in mixing problems. Okay, so here's our model right here. We know that the rate at which our substance comes in and the rate at which it leaves is proportional to one another, and they're equal to 8 liters per minute. We know that the concentration of the substance coming into the tank is 0.05 kilograms per liter, and we know that we have an initial volume of 100 liters. And so if we plug this all in here, we're going to get this. We're going to get 8 liters per minute multiplied by 0.05 kilograms per liter. And you can kind of see how the units are going to cancel there. So the rate at which salt is entering the tank now, and this is why this is actually the case for this formula, right, is going to be 0.05 kilograms per minute, right? Every minute we get 0.05 kilograms of salt enter into the tank. And then we're going to subtract 8 liters per minute, the rate at which the salt leaves the tank, times this variable concentration of a different amount of salt divided by 100 liters, right? Because if we put something with a different concentration into the tank, then the concentration of the liquid that's going to leave, if we mix them together, is going to be different than the concentration that entered into the tank. And so that is where that is coming from. We're getting a different rate of change for the bottom half here, Q of T kilograms per minute, but that's still going to be a rate at which salt is leaving the tank. And we want an expression in general for the rate of change of the salt, and so we can just kind of go from there. But that kind of gives you a little bit better of an idea of why we chose the equations that we did. Okay, and then we have this initial condition from the question, Q of 0, so Q, the amount of salt in the tank at time 0 is equal to 0.5 kilograms. And then the rate of change of the salt at any given point in time can be simplified to 2/5 minus 2 Q of T over 25. Okay, now I took the units away. We're going to keep in mind that everything on the right-hand side of the equal sign is kilograms per minute. 2/5, that's the same thing as 8 times 0.05. And 8 divided by 100, that's the same thing as 2 over 25. So I've just written it in a form we're a little bit more familiar with. What I'm going to do now is I'm going to multiply both sides by 25. You'll notice that when I do that, I get 25 dq dt is equal to 10 minus 2q of t. So I kind of skipped a couple of steps here, and I've done a couple of them at the same time. But once we have that 25 dq is equal to 10 minus 2q dt, I'm just going to divide that 10 minus 2q over to the left-hand side and keep that dt over to the right-hand side, which technically had been multiplied over there, I guess I should mention. Then once we've separated those variables, we're going to integrate. Now, it's not always going to be the case for questions like these ones that it's going to give you a separable equations. Sometimes the amount of water is going to be variable as well in the tank, and that's going to require us to use an integrating factor, which is a whole other monster, but it's not terrible. And so it's kind of nice that in this case we just have to deal with a linear separable differential equation. Okay, I end up with these two integrals. I'm going to do a substitution for the integral on the left where I say u is equal to 10 minus 2q, so that du is equal to negative 2 dq, and then negative 1/2 du is equal to dq. I can plug all of that in so that on the left-hand side I get negative 25 over 2 integral of du over u is equal to t plus c. and that t plus c is just coming from the fact that the integral of dt is t plus c. Now the integral of du over u is natural logarithm of u, and u is equal to 10 minus 2q, so that's where the negative 25 over 2 ln of 10 minus 2q is coming from. From here, what I want to do is I want to multiply both sides by negative 2 divided by 25, so that I just get a natural logarithm by itself on the left-hand side. And then I want to exponentiate both sides. So that's where this next step is coming from, this e to the ln of 10 minus 2q, and then this e to the power of negative 2t over 25 plus c. On the left-hand side, after I've done those two steps, the e and the natural logarithm are going to cancel out. I'm just going to get 10 minus 2q. And then that's going to be equal to e to the power of negative 2 over 25t plus c. But then I'm breaking the e to the c kind of out of there at the same time, so that it's just e to the c times e to the negative 2 over 25t. And then I redefine my constant, because my constant is arbitrary, to just be c e to the negative 2 over 25t. And so what I'm going to have for my solution is I'm going to have that q of t is equal to 5 minus c e to the negative 2 over 25t. Now, obviously, with differential equations, we have families of solutions that depend on our initial conditions. And so the last step is to apply our initial condition, which, when we do so, is going to give us that 5 minus c is equal to 0.5. And so c is 4.5, which is 9 over 2. Okay. Now that was kind of a mouthful too, but now what we need to do is need to answer the question that we were given in the beginning by taking a look at our equation that we've been given. So we know that the amount of salt in the tank at any given point in time, with the concentrations and the information that we were given, should be equal to 5 minus 9 over 2 e to the negative 2 over 25t. And just for the sake of making things a little bit more visual, I've put the graph up onto the board here as well for the solution to the differential equation, and you can see how it's going to kind of start growing. And then I've put this little blue line here to kind of symbolize how the concentration, or the amount of salt in the tank, is kind of just going to level off eventually. The reason being is because if we were to take the limit as t goes to infinity, so as time goes on forever of the solution that we just found, eventually everything in the tank is just going to turn into salt, because, okay, we started out with half a kilogram of salt in 100 liters, right? That's a concentration of 0.005. And then we input a solution that has a concentration of 0.05, so 10 times as much concentration of salt in this solution we're pouring into the tank than is already in there. And so it only makes sense that over time, everything is just going to become salt, right? And so the limit is equal to 5. Makes sense that if the y-axis here represents the amount of salt in the tank in kilograms, and the x-axis represents the time, that we're going to only end up with 5 kilograms of salt in there as time goes to infinity. But that wasn't the question we really had to worry about. We wanted to know at what point in time would the concentration in the tank be equal to 0.02. Now, what is that equal to? Okay, well, I'm going to have 2 kilograms of salt in the tank at that particular point in time, because concentration being equal to 0.02, that's the same as 2 divided by 100, and 2 divided by 100 is 0.02, right? 2 kilograms divided by 100 liters. And I put the arithmetic down here on the bottom here that we could go through to come up with this particular value, 5.068, which is measured in minutes. Basically, all we do is we just set this equation we have equal to 2, right, to figure out at what point in time we will have 2 kilograms of salt in the tank. We move things around a little bit, and eventually end up having to use the natural logarithm to get that t is equal to negative 25 over 2, natural logarithm of 2/3, and that's about 5.068 minutes. So after 5.068 minutes of this liquid pouring into the tank and another liquid leaving the tank that has a different concentration than the liquid that we were pouring into the tank, or the liquid that was already in there, we are going to end up with 2 kilograms of salt in the tank, meaning that we will have a concentration of 0.02 kilograms per liter, given that the amount of water in the tank is constant, right? If we're pouring in at a rate proportional to the rate that it's leaving, then we're always going to have 100 liters of water in there. And so at any given point in time, we can take an amount of salt and divide it by that volume to get the concentration. Awesome. I hope that was helpful. If you have any questions, feel free to email me or send me a text message. I have my contact information on the screen. Yeah, looking forward to talking to you later.